In last video, we studied about relation. So what is a relation? A relation R, if it is defined from A to B, is said to be a relation from A to B if so R is equal to X comma Y is said to be a relation from A to B if all the X belongs to A and all the Y belongs to B. Now, there are certain formulas that we need to remember. The first formula is the number of relations. The number of relations is given by the formula 2 raised to the power mn, where m is the number of elements in the set A. M is the number of elements in the set A, and n is number of elements in the set B. So suppose set A has 3 elements, set B has 2 elements, then 2 raised to the power 3 into 2, m into n, 2 raised to the power 6, that is 64 relations are possible from A to B. We can have 64 relations from A to B. So number of relations from a set A to the set B is given by the formula 2 raised to the power mn, where m is the number of elements in A and n is the number of elements in B. Suppose R from A to A is a relation such that A has n elements. Then A part, number of reflexive relations. Number of reflexive relations is given by the formula 2 raised to the power n into n minus 1. So the number of reflexive relations is given by the formula 2 raised to the power n into n minus 1. Similarly, number of symmetric relations is given by the formula 2 raised to the power n into n plus 1 upon 2. So we need to remember these three formulas. The number of relations from A to B is 2 raised to the power mn. The number of reflexive relations on A is 2 raised to the power n into n minus 1. And the number of symmetric relations on the set A is 2 raised to the power n into n plus 1 by 2. Now I'm going to give you an example. Suppose set A has 5 elements. That is, number of elements in A is 5. And if you have been asked the number of reflexive relations on A, number of reflexive relations on A is given by the formula 2 raised to the power n into n minus 1. So 2 raised to the power 5 into 4, which is 2 raised to the power 20. So 2 raised to the power 20 will give me the number of reflexive relations. And if you have been asked to find the number of symmetric relations, then the number of symmetric relations is given by the formula 2 raised to the power n into n plus 1. Now here in this case, n is 5, so 2 raised to the power 5 into 6, upon 2. 2 raised to the power 5 into 6 upon 2. So that is going to give me 2 raised to the power 15. So there are 2 raised to the power 15 symmetric relations on A, where A has 5 elements. Now, the second thing that we need to do in 1.1, which is not mentioned in NCERT, is to find out equivalence class. Now, what is equivalence class? Suppose a relation R is defined as A comma B such that A plus B is equal to 6 and A and B both belongs to the set A, where the set A is defined as 1, 2, 3 up to so on 10. Now the question could be anything. The question could be that find the equivalence class of a particular number. So first of all, we will write the relation in roster form. If we take the value of A as 1, I'll get the value of B as 5. I'll get the elements of R as 2, 3. then I'll have 3 comma 2, then I'll have 4 comma, sorry, 3, the sum should be 6. So 2 comma 4, it should be 2 comma 4, 3 comma 3, 4 comma 2, 5 comma 1. These are all the elements in the relation R. Now, if the question is, find the equivalence class of 1. So find the equivalence class of 1 means I need to take the value of A as 1 and I need to find all the possible values of B. So if I take A as 1, so the B can take only one value, which is 5. So I'll write that 5 is the equivalence class of 1. So all the possible values of B are called the equivalence class of a particular relation, a particular number. Now, I'll give you one more example. So first of all, we are going to write the definition of equivalence class, or we can say the step to find out the equivalence class. If you have been asked, to find equivalence class of a number, say x, then take A as x and find all possible values of B. Find all possible values of B. Those values of B taken together, is called equivalence class of X. I repeat, if you want to find out the equivalence class of a number, what you need to do is you need to assume A as X. Then find out all the possible values that B can take and the set of all those possible values of B. Those values of B taken together is called the equivalence class of X. Now I'll give you one more example about it. Suppose the question is that A is a set given by X is an integer, X lies between 0 to 12. So I can clearly say that A is given by the set 0, 1, 2 up to so on 12. Suppose the relation R is defined on A as R is equal to A comma B such that modulus of A minus B is a multiple of 4. And if the question is find equivalence class of 0, find equivalence class of 2, find equivalence class of 5. So first, let us find the equivalence class of 0. Let us take A as 0. And now we need to find out all the possible values of B. So for A comma B to belong to R, we should have modulus of A minus B is a multiple of 4. Modulus of A minus B is a multiple of 4. If we put the value of A as 0, so modulus of minus B, which can also be written as B, is a multiple of 4. So what are the possible values that B can take? Out of 0 to 12, which is the set A on which the relation is defined, what all numbers are the multiple of 4? 0 है, 4 है, 8 है, 12 है. सिर्फ यही numbers हैं जो 4 के multiples हैं. So I'll write these numbers. So this set is the equivalence class of 0. This particular set is the equivalence class of 0. Now we'll move to the next question. We'll find the equivalence class of 2. So if we want to find out the equivalence class of 2, we will write let A is equal to 2. That means modulus of 2 minus B should be a multiple of 4. Modulus of 2 minus B should be a multiple of 4. Now, what are the values that B can take so that modulus of 2 minus B is a multiple of 4? So, first value that it can take is 2 because 2 minus 2 is going to give me 0. The next value it can take is 6 because 2 minus 6 will give me 4, which is a multiple of 4. The next value that B can take is 10 because 2 minus 10 will give me 8, which is a multiple of 4. Then after that, after 10, what I need to take is 14, but 14 is not in A. So I'll just close this bracket and I'll say this is the equivalence class of 2. So the equivalence class of 2 is 2, 6, 10. So this is how we can find out the equivalence class of any number for a particular relation which is defined, which is given to us in the question. Now we'll move to the last part of this question, which is we need to find the equivalence class of 5. So let us find the equivalence class of 5. So in order to find the equivalence class of 5, we will write let A is equal to 5. So for A comma B to belong to R, we should have modulus of 5 minus B is a multiple of 4. Modulus of 5 minus B is a multiple of 4. So let us see what are the possible values that B can take so that modulus of 5 minus B is a multiple of 4. Let's start from 0. 5 minus 0, then we'll move to 1. 5 minus 1 will give you 4, which is a multiple of 4. Then 2, 3, then we'll move to 4, then 5. 5 minus 5 is going to give me 0, which is a multiple of 4. So I'll take 5 as my element. Then next multiple, if I put 6, I'll get 1. If I put 7, I'll get 2. If I put 8, I'll get 3. If I put 9, 5 minus 9 will give me 4, which is a multiple of 4. Now the next number that I should put here is 13. But 13 is not there in the set A, so I'm going to close this bracket. So this set which I have got, 159. The set which I have got, 159, this set is the equivalence class of 5. So in this way, we can find out the equivalence class of any number. We just need to take A as that number, and then we need to find all the possible values of B. Now, the next extra question that can come from exercise 1.1 is, let R be a relation defined on A cross B to B cross A, and suppose the relation is defined as, follows, that AB is related to CD if and only if A plus D is equal to B plus C. And question is, check whether the given relation is equivalence relation or not. Check whether the given relation is equivalence relation or not. Now, we have not seen such kind of relation in our NCERT. So how to, first of all, we need to understand what this type of definition is. So basically, how do we write our element? We write our element as AB belongs to R. We have never seen our elements written as A, B, R, C, D. So basically here A, B, R, C, D means that AB, comma, C, D belongs to R. It means if I write X, comma, Y belongs to R, so here X is A, comma, B, and here Y is C, comma, D. This is what it means. Why? Because this set is A cross B, and any element of A cross B is of the form A, comma, B. And sorry, this is defined from A cross B to A cross B. And any relation here, A comma B is of the form A comma B. So we can say that ABRCD means that basically AB, comma CD, whole bracket belongs to R. So this is our X and this is our Y. So one element, the domain is of the form A, comma B. The range is of the form C, comma D. This is what it means. Now, first of all, we'll check and what is the relation? The relation is defined as A plus D is equal to B plus C. That means we are going to take the first element, we are going to take the last element, we are going to add them. Equal to, we are going to add the middle two numbers. So let's move to the reflexive part. So for reflexive, what do we need to show? For reflexive, we need to show that AB is related to AB. Basically, what do we show? We show X comma X belongs to R. So here X is A comma B, X is A comma B. Therefore, we need to show AB is related to AB. So exactly what do we need to show? The sum of first and the last element, this is 1, 2, 3, 4. The sum of the first and the last element, which is B in this case, is equal to the sum of the middle two terms, which is B plus A. This is what we need to show. But we know that the commutative property of addition says that A plus B is equal to B plus A. Hence, this relation is reflexive. So we will write by commutative property of addition, or we can, instead of by, we can write using commutative property of addition, we can say A plus B is equal to B plus A. This implies AB is related to AB and therefore our relation R is symmetric. Sorry, is reflexive. Therefore, our relation R is reflexive. Now we'll move to the symmetric part. The symmetric part says, if X comma Y belongs to R, then Y comma X should also belong to R. So, in order to prove the part symmetric, we will write, let A comma B be related to C comma D, which means A plus D is equal to B plus C, and we need to show that it is symmetric. That is, we need to show that CD is related to AB. That is, we need to show that sum of the first and the last term, which is C plus B, is equal to the sum of the middle two term, which is D plus A, which is by default true. If A plus D is B plus C, then C plus B is D plus A, which is by default true. So we will write that A plus D is equal to B plus C. This implies C plus B is equal to D plus A. Therefore, our relation R is symmetric. Therefore, our relation R is symmetric. Now, in order to prove that the relation R is transitive, how can we prove that our relation R is transitive? So third part is we need to prove that the relation R is transitive. So transitive ke liye what do we show? X comma Y, Y comma Z belongs to R. We need to prove X comma Z belongs to R. So we will write let AB be related to CD. Let CD be related to EF. And what do we need to prove? We need to prove that AB is related to EF. AB related to CD implies A plus D is equal to B plus C. CD related to EF implies sum of the first and the last term is equal to the sum of the middle two terms. So we'll mark this as 1, we'll mark this as 2. And what do we need to prove? We need to prove sum of the first and the last term is equal to the sum of the middle two term. We need to prove that A plus F is equal to B plus E. How can we do that? The two results that we have got, 1 and 2, we are going to add them. Add 1 and 2. So if we add them, I can say A plus D plus C plus F is equal to B plus C plus D plus C. Now I'm going to cancel it. C will get cancelled with C, D will get cancelled with D. So I can say A plus F is equal to B plus E. Hence, our relation is transitive and hence it is proved. So by adding the two results that we got from the given, we got the result that AB is related to EF, and hence we conclude that it is a transitive relation, and hence our given relation is an equivalence relation. Now the second type of question is related to this only. R is defined on n cross n to n cross n. R is defined as R AB is related to CD if and only if AD is equal to BC. Now try and understand the relation. It is AD is equal to BC. That is the product of the first and the last term is equal to the product of the middle two terms. So first we are going to check for reflexive. For reflexive, we need to see whether AB is related to AB or not. Product of the first and the last term is AB, product of the middle two term is BA. So again, we can say by using the commutative property of multiplication. By using commutative property of multiplication, by using commutative property of multiplication, we can say that AB is BA. Therefore, we can say that AB is related to AB, and therefore our given relation is reflexive. Now for the symmetric part, we will write let AB be related to CD. This means AD is equal to BC. And what do we need to prove for the relation to be symmetric? We need to prove that CD is related to AB. That is exactly what do we need to prove? We need to prove that the product of the first and the last term CB is equal to the product of the middle two terms, which is by default true. So we can say AD is equal to BC implies that CB is equal to DA. Therefore, our relation R is symmetric. Now we'll move to the third part, which is transitive. So for the third part, transitive, we will write let AB be related to CD. Let CD be related to EF. And what do we need to prove? We need to prove that AB is related to EF. So AB related to CD implies the product of the first and the last term is the product of the middle two term. CD is related to EF implies product of first and the last term is equal to product of the middle two terms. And what do we need to prove? So exactly we need to prove that AF is equal to BE. Now how can we prove that AF is equal to BE using 1 and 2? Like in the previous question, we added two results. Now in this question, we'll multiply both the results. So we are going to write multiply 1 by 2. So we can say ADCF is BCDE. D will get cancelled with D, C will get cancelled with C, and then we can say AF is equal to BE, and therefore we can conclude that R is transitive R is transitive, and so we can say that R is an equivalence relation. Now, the question of equivalence class can also be asked in this question. So if in this question you have been asked to find out the equivalence class of a particular number which is of the form a comma b, then how can you find out that? So if in this particular question you have been asked to find out the equivalence class. So if the question is find equivalence class of 1 comma 2. Now here the element will be of this form because one element is of the form a comma b. So the question is find the equivalence class of 1 comma 2. So in this case we'll take a comma b as 1 comma 2. So we can say a is 1 and b is 2, and we need to find all the possible values of c comma d such that ab is related to cd. So let ab be related to cd. This implies 1 comma 2 is related to CD. So product of the first and the last term is equal to the product of the middle term. So D should be equal to 2C. So since they are derived from the natural numbers, so if I give the value 1 to C, the value of D will be 2. For 2, it is 4. If I take value of C as 3, I'm going to get D as 6. Then for A4, I'm going to get 8 and so on. Because it is defined on natural numbers, so it will be an infinite set. So this set is the equivalence class of 1 comma 2. So in these type of questions also we can find out the equivalence class. Now, the third type of question that can be asked related to this is, let R be a relation defined on n cross n to n cross n, and it has been defined as AB is related to CD if and only if AD B plus C is BC A plus D. Now, please understand the pattern. The pattern is product of the first and the last term into the sum of the middle two term is equal to the product of the middle two term into the sum of the last two term. So this is the pattern that we need to understand. So in order to prove that it is reflexive, we are going to write consider A comma B related to A comma B. Let's make a pattern. The product of first and the last term is AB. The sum of the middle two term is B plus A. The product of middle two term is BA, and the product of first and the last term is A plus B. Now, clearly we can say that these two are equal. So we will write clearly these two are equal because AB is equal to BA, B plus A is equal to AB. By commutative property, we can say they are equal. Therefore, the relation R is reflexive. Now, second part is, in order to prove that this is symmetric, we will write let AB be related to CD. Now, if AB is related to CD, what does this imply? This implies AD into B plus C is equal to BC into A plus D. So what do we need to prove? We need to prove that CD is related to AB. Let's make a pattern. That is, we need to prove product of the first and the last term into sum of the middle two term, D plus A, is equal to DA into C plus B. This we need to prove, which is by default true by the given statement, which is true from 1. This will mark as 1. So this is true from 1, and therefore we can say that our given relation is symmetric. Now its transitive part is a bit different. Like in first question, we added both the results. In second question, we multiplied both the results. Now let's see how we can prove the transitive part of this question. इस क्वेश्चन का ट्रांजिटिव पार्ट देखते हैं कि हम कैसे सॉल्व कर सकते हैं. So we will write, let AB be related to CD and CD be related to EF. अब AB related to CD है, इसका मतलब AD into B plus C is equal to BC into A plus D. CD related to EF है, इसका मतलब CF into D plus E is equal to DE into C plus F. And we need to prove that AB is related to EF. That is, we need to prove AF into B plus E is equal to BE into A plus F. Now, how can we prove that? If we add both the results, we are not going to get what we want. If we multiply both the results, we are not going to get what we want. So what we are going to do is take the first statement, which is AD into B plus C is equal to BC into A plus D. Cross multiply. Shift AD to right hand side and shift BC to left hand side. So B plus C by BC is equal to A plus D by AD. So if we split the numerator, we are going to get B by BC plus C by BC is equal to A by AD plus D by AD. B will get cancelled, C will get cancelled, A will get cancelled, D will get cancelled, and we are going to get 1 by C plus 1 by B is equal to 1 by D plus 1 by A, and we are going to mark this as 1. Again, we are going to do the same thing with the second equation that we have. That is CD is related to EF. With CD related to EF, we are going to do the same thing. I'm just keeping this 1, which I have marked, and I'm keeping this, which we need to prove. We need to prove AF into B plus C is BE into A plus F. This is what we need to prove. So I'm just keeping this. Now, we have CD is related to EF, which simply means CF into D plus E is equal to D into C plus F. We are going to do the same thing. We'll shift CF to right hand side and we'll shift D to left hand side. So D plus C upon DE is equal to C plus F upon CF. Now we are going to split it. D upon DE plus E upon DE equal to C upon CF plus F upon CF. D will get cancelled, E will get cancelled, C will get cancelled, F will get cancelled. And we are going to get 1 by E plus 1 by D is equal to 1 by F plus 1 by C. We are going to add both the results. If we add 1 and 2, 1 by C plus 1 by B plus 1 by E plus 1 by D is equal to 1 by D plus 1 by A plus 1 by F plus 1 by C. 1 by D will get cancelled. 1 by C will get cancelled. So whatever we are left with, we have to take the LCM and shift the product to right hand side to get our result. So we'll take the LCM. BE, if we take the LCM, I'll get E plus B upon BE is equal to A plus F upon AF. Cross multiply. AF into B plus E is BE into A plus F, and this is what I need to prove. And therefore, we can say that the relation R is transitive, and hence our given relation is equivalence relation.